Good day and welcome back for the second part of our discussion of changes of variables for evaluating double integrals. In our previous video, we introduced the idea of a change of variables and we investigated several common types of examples. In this video, what we would like to do is specifically come up with a formula of how we can use a change of variables to hopefully simplify a double integral and make it easier to evaluate. But before doing so, we need to introduce a new concept. We need to talk about the Jacobian of a change of variables. So if we have a change of variables given by x is equal to g of uv, y is equal to h of uv, then the Jacobian, something that we refer to as partial xy over partial uv, is a 2 by 2 determinant. The top row of the determinant comes from taking the first variable x, differentiating with respect to u for the first entry, v for the second entry. And then the same idea with y's for the second row. And how I remember this is that we have xy vertically, and then we have uv determining the columns. So as we proceed horizontally through that 2 by 2. And when we calculate this determinant, we multiply down the main diagonal, partial x, partial u, times partial y, partial v, and we subtract away what we get when we multiply down the cross diagonal. And note it looks rather abstract at the moment, but for a nice concrete example, this idea will become more clear. And let me make one more observation about the formula. Depending upon the example, it may not be convenient to calculate the partials in this order, but instead we might want to flip the partials. That is, we might want du dx and du dy instead, going across that top row, which leads to this opposite Jacobian. And what I want to note is that these Jacobians actually behave much like fractions in the sense that this would be simply 1 over partial xy, partial uv. That is to say, if you want to switch around notationally the numerator and the denominator of the Jacobian, that's just, in a sense, taking its reciprocal. At this point, the change of variables that we are familiar with would be polar coordinates. So let's find that associated Jacobian. With polar coordinates, we think x is r cosine theta, y is r sine theta. And I would like to find the Jacobian partial xy, partial r theta. And I'm going to just write out the 2 by 2 determinant in terms of partials. So we would have partial x, partial r. So I'm taking the first variable in the top, and we'll calculate the partials with r and theta across that first row. So partial x, partial theta. And then the second row, we use that second variable in the top, y. And these are nice, quick partial derivatives for us to calculate. The partial derivative of x with respect to r is cosine theta. The partial derivative of x with respect to theta would be minus r sine theta. Similarly, for y, we have sine theta and r cosine theta. So that the Jacobian would be the 2 by 2 determinant. We multiply down the main diagonal. We subtract away what we get when we multiply down the cross diagonal. But we're subtracting away a negative, so minus a minus becomes a plus r sine squared theta. So r cosine squared plus sine squared. Remember, cosine squared plus sine squared is 1, and we end up with an r. This directly leads us into our change of variables formula for double integrals, but I will note when you look through the textbook, you'll see that there is an identical formula for multiple integrals, whether it's double, triple, or more. We will just focus on the double integral version purely to make the computations as convenient as possible. Because as we'll see, these problems can certainly be a bit involved. So if we have a double integral over a region R, and we have a transformation that's taking us into, say, the UV plane, so we're changing our variables, and our region becomes S. That region S would be the new region of integration, and then we need to simply rewrite everything in terms of these new variables. That is to say, each x needs to be written in terms of u and v, each y needs to be written in terms of u and v. And then the new part here is that the dA is going to become the absolute value of the Jacobian that we've defined above, and then it's du dv. And if we think to polar coordinates, you'll immediately make that observation that r in polar coordinates is playing the role of the absolute value of the Jacobian. And I will also emphasize that this really is the absolute value, so if it's a negative quantity, you need to make it positive for this formula to work. Let's go ahead and apply this to a nice concrete example. A typical example involving a change of variables is made up of a double integral that we would like to evaluate. Sometimes, such as the problem here, we will give you the change of variables, while in other examples we will have to generate or come up with the change of variables ourselves, but it will only be in precise scenarios. So in this case we have the double integral over a region R, which is a parallelogram in the xy plane sketched to the left. And we will use the change of variables provided to evaluate this double integral. Now remember, the reason we want a change of variables is that for some reason this integral is maybe difficult to evaluate directly. That could be because the function is difficult to integrate, or the region is not something that we can conveniently describe. And this certainly falls into the latter case, where the region is just not all that simple to describe if we're thinking of type 1 and type 2 regions. Note, if you wanted to think of this as, let's say, a type 1 region, we would have to break it up into two pieces. You would have to look to the left of 1, and we can see the region varying nicely between functions of x. Then you'd have to look to the right of 1, where it's varying between different functions of x. So if we wanted to evaluate this directly, we certainly could, but it would require us to evaluate two double integrals. In this case, we're going to go ahead and use the transformation, and note if you are ever asked to specifically use a change of variables or use a specific technique for a problem, you certainly should do so in order to receive full credit. Now, in order to proceed with this example, there's kind of two main things that needs to be done. We need to figure out how is this region of integration going to be modified, and then how do we modify the integrand, i.e. there will be a Jacobian that needs to be calculated. Let's start off with the region of integration. So the first thing that we want to think about is how will our region be modified under this transformation. We have x is equal to 1/4 u plus 1/4 v, and y is equal to minus 3/4 u plus 1/4 v. And we would like to sketch what will the corresponding region become in the UV plane. Similar to our first example in the previous video, we are going to take our region of integration and break it down into its 4 individual sides. And if we can figure out what happens to each side individually, that should give us a very clear idea of what is going to be happening to the entire region itself. So if we start off with the first side, we have y equals x minus 4. And to express this in terms of the new variables u and v, we simply need to rewrite each x and y according to our transformation formulas. So y will become minus 3/4 u plus 1/4 v, while x will become 1/4 u plus 1/4 v. And note we immediately see 1/4 v can be subtracted from both sides. And we can also add 3/4 u. Oh, and I have a -4. So we can add 4 to both sides and add 3/4 u to both sides. So side 1 is going to go to the line segment u equals 4. And this will be side 1. And now we just keep playing this game. If we look at side 2, the equation is y is equal to 8 minus 3x. So the y would be minus 3/4 u plus 1/4 v. And then minus 3x would be minus 3/4 u, I'm distributing the minus 3, minus 3/4 v. So similar to our above computations, we can add 3/4 u to both sides. And we can also add 3/4 v to both sides to end up with v equals 8, which is a horizontal line segment, which corresponds to side 2. And what I'm going to note is I'm not going to go through all of the computations here because I think this would be a great opportunity for you to fill in those details. But if you do, side 3 is going to go to the vertical line, u equals -4. And side 4 is going to go to another horizontal line, which is awfully convenient, v equals 0. And we now have a much more convenient region of integration in terms of u's and v's. In order to evaluate the double integral, let's just kind of think about what it's going to look like, and that will tell us what other quantities we need to compute. So if we have the double integral over r of 4x plus 8y, we're going to have a new region of integration, this rectangular region S we've determined, along with rewriting. So every x we see has to be replaced with 1/4 u plus 1/4 v, and every y needs to be replaced with minus 3/4 u plus 1/4 v. Now on top of that, remember we need to calculate a Jacobian. The Jacobian we need would be partial xy over partial uv in absolute value, and now our new variables of integration will be du dv. And note when I write du dv here, this is in the generic sense corresponding to s. I'm not saying we have to integrate in this order. So we have one more quantity to determine, and then we'll be good to go. That is, what is this desired Jacobian? So the partial xy, partial uv, and our formulas are written nicely above for the transformation in order to calculate these partials. Working across the top row of our 2 by 2 determinant, we will have the partial of x with respect to u, and then the partial of x with respect to v, which would be 1/4 and 1/4 respectively. And we do the same thing across the bottom row, but we are taking the partials of y with respect to u and respect to v. We calculate this determinant by multiplying down the main diagonal, so 1/4 times 1/4, and we subtract away what we get when we multiply down the cross diagonal, which would be 1/4 times minus 3/4. 1/16 plus 3/16 is 4/16, which is maybe more conveniently 1/4. And that quantity 1/4 is what we substitute in for our Jacobian. So let's go ahead and convert this into an iterated integral that we can hopefully easily evaluate. So the first thing is to note that in our integral we need to distribute through the 4 and the 8. When we do so, we'll end up with a 3v minus 5u. We have a 1/4, our Jacobian. And I'm going to go ahead and leave the order as du dv. And note if we look above, we saw u in our rectangle varied from -4 to 4. And v varies from v equals 0 up to v equals 8. And once we get it to this point, this is a very reasonable double integral to evaluate. And instead of going through all of the details, which we will do occasionally, I'm going to leave this work up to you, but please do double check, and you should get 192. So in this first example, I want to note the key elements to the problem. We have to figure out how the region is transformed, which we've done to find this nice rectangular region S in the UV plane. And we also need to determine the Jacobian. But once those are identified, we have a double integral that becomes convenient and efficient for us to evaluate. In the next video, we'll investigate another, what I'll call common example related to changes of variables. So stay tuned and take care.